All right, let's talk about switch capacitor design and how we can do programmable analog circuits rather than hardwiring resistors and capacitors. So at the heart of this technology is taking something called a switched capacitor, which is effectively a programmable resistance. And how is this done? Well, you have a capacitor and you have a switch 1 that opens and closes with a frequency of Fs, and switch 2, which opens and closes with a frequency of Fs, as seen over here. And just something important is that they're never on at the same time. So what I've drawn is a signal going up, which would close switch 1, switch 2 is open, and then the reverse is true. So we have charge on a capacitor, and the Q in, right, is just V in times Cs. Q out is V out times Cs. Now we want to have a rate of change here, and we're going to call it a current because that's kind of effectively what it is. And so we have the current, and then we have this rate, which is the clock, right? So what is Q? The total Q, Q in minus Q out. And we substitute these equations in here, right? V in minus V out, and we have our capacitance and our switching frequency. And then to show that it's an effective resistance, we're just going to call this V, all right? And then we will notice there's our I, V, and a scaling factor. Well, if we solve for resistance, or in this case of equivalent resistance, we get 1 over CS Fs. And this can be changed. Sure, on the chip the capacitor would be fixed, or you could be selecting between different fixed capacitors, but all you have to do to change the equivalent resistance is change how fast that clock is going, which can be done in the technology I'm about to show you, even after you've programmed it. All right, so what does this look like when we're using it? Well, if you know an inverting op amp, right, it's the same structure, except now the resistances are programmable. So you have a kind of just a triangle symbol with a minus gain stage. Right here we have an inverting summer, and everything can be programmable. Everything's inverting, and you can actually have each line coming in with an independent gain. And here we have an integrating inverter, right, which you can use, an inverting integrator, excuse me, which you can use the integrating symbol, or sometimes we like to use 1 over S. Now, yes, the equation's really minus 1 over RC, right? That would be the feedback, and this R would be the one that's programmable. And so rather than when you're doing a circuit, rather than using these actual circuit parameters, you can use kind of like signal flow blocks, all right? Now there is something that you need to know for later, is that I've kind of shown you everything with one output. These switch capacitor circuits are differential in nature, so you get a plus output and a negative output. But for what I'm showing you today, it's not so important. So let's just do a quick example of a state space filter, right? And, you know, I just put my summer here. I have an integrate symbol, an integrate symbol. The integration constant needs to be A1, and then that's feeding into the next integrator. I want A2, but that means it's that integration constant has to be A2 divided by A1, so that when I multiply these through, the A1s cancel out, right? Now, sure, the negative feedback that's used, in they'd call it minus A1, minus A2, but really, everything in this case is non-inverting. It'll be positive, and then here at the summer, you would just say inverting, with a gain of 1. All right. Now, for the example, I wanted a cutoff frequency of 10 kilohertz. And I used Python to give me a Butterworth response. So the damping factor is 0.707. And so here it's 0.044. You'll see when you use the tool that it pre-scales it. So it's 0.004 divided by 1 e to the minus 6. And then this one is 0.0899 divided by 10 to the 6. And I just want to double check that I've got that right. Nope, it's backwards. So this constant is that integration constant, and that one goes there. All right. So you can use the Anadigm software actually before you have purchased your board. And so there's a download center, and you just have to make an account and log in and download and open up the software. And it'll give you a default chip. And this is the chip that comes with the board now, the current system. So the first thing we do is we have to kind of have some kind of input. So you click on that, and everything is called a CAM, configurable analog module. And that will allow me to tell you what it is. It could be an input, could be output, independent amplifier. We're just going to put in an input. And this time we're just going to do bypass, although you can do other options as well. So we needed a summer, so we insert a new CAM, configurable analog module, and let's find a sum diff. That means you can add and subtract. Now, it's a half cycle, which I'll show you what's important about that later. But the first input we want non-inverting, the second we want inverting, and the third and fourth inputs are normally off. So these we want inverting, and so since the gains are 1, that's really -1, -1. So now we set up that summer. Now we need our integrators. Integrator. All right. Now if you notice here, it's got a green like stop sign symbol. That means I can't place it there. So you have to find a spot to place it. And then it'll pop up. Now, you have the option of making these integrators non-inverting, inverting, or non-inverting. I'm just going to keep it non-inverting. There's a clock, and we want things to happen on the first clock, and there's the clock frequency. Now, here's that integration constant, right? And everything is scaled by a microsecond. So really, that's going to be 0.0889. We'll add another CAM. And it can get a bit the wires, you don't actually have a lot of control over how they appear, and you'll have things that cross. It's not like Spice where you can give things net names. So we have the output of the summer. Oops. That's the oscilloscope probe. You just hover over it and left click and let up and draw your line. Left click, hold up. All right. This is the output of the first first integrator. And then you'll see that in order, like I'd like to route it without crossing, but it won't let you, select as you go. You just end up going right there and seeing it like that. And then you can connect the input. And actually looking right now, it looks like I did not invert that input 3. All right. So now we can see that. And if you recall, this would be the output of the low pass node. So let's just wire up the chip so that's the output. Okay. So this is going to be a real chip, and so you have to check to make sure you haven't violated any rules. So if you do file check sheet, it'll give you, it's saying that everything is fine. Okay. Which at this point you would load it into your board. We're just going to simulate it today. We're not configuring the board. But to simulate, we need a input. And so let's, these tools don't have a transient, so they won't really do a Bode plot right off the bat. So if we have a 10 kilohertz cutoff frequency, that means if we do square wave at 2K, we should be able to see. Now it's not an actual tau, it's a second order system, but that should work so that we can see the rise and the fall time. All right. Now these are the oscilloscope probes, and even though it's differential, when we take the output, internally you can just click on a node and plot unipolar. All right. Configure our simulation or set it up. I guess I had it set up for something before. And just this little button here, left click on simulate. And we see the step response of a low pass filter. We see a little bit of overshoot, so it's definitely underdamped. Now, if you recall, right, that would be the low pass node. This would be the high pass node. So let's put an oscilloscope probe here. Now, you might notice that it's fuzzy here, so let's zoom in. And you see that it's on and it's off, it's on and it's off. And that's because this is a half cycle summer, and you need a sample and hold to actually smooth these values out. Now, the values are still analog, but they're discrete time. And so we need to put a sample and hold there. But before we do that, I'm going to show you an actual error. Okay. So let's say I want to take that out, the high pass from this node, the low pass from this node. And we're going to check sheet and say cam phase mismatch. So we have something that's only valid every half cycle being put off chip. Maybe you want it that way, but chances are you don't. So you need to add a cam, and it's just a hold. All right, so that makes sure that holds it so that when it goes off for one cycle, all right, so let's move this here. Let's check our simulation, check our sheet. Design, everything passes, great. So if we were to simulate, that kind of behavior goes away, and you can see that it's definitely detecting an edge, right? But that there's an undershoot, or it detects a negative edge and then there's an overshoot. So it's still the same, the polynomial of the denominator is the same as you would expect. Now, this shows how this tool can be used, but really they have much higher order things that you can use. And so if you really want to try to use the highest order thing that you can, and I am looking for a filter, biquadratic filter. Okay. Now look, you can click low, high, band, whatever you would like. All right. Here's a corner frequency. You have the gain, and then there's the quality factor or the damping ratio. So if you really needed a filter, this is the way to do it. Now, sure, a state space filter would give you control over other things, but if you're doing a, this kind of filter, this is the way to go. And it looks like you can do poles and zeros as well. All right, so you have a lot of control, but it's still a second order. Type 1 and type 2, that's internal, I believe, to the tool using the switch capacitors. All right, and let me just bring up my other design. And yes, I pretty much showed you everything. Other things that we can look at is here's a way to do a Schmidt trigger, right, which is made out of an op amp with positive feedback. But the way you would do that is actually you have a summer, which has gains, and then you have a comparator, which is like an op amp with no feedback. And so this is one way to do a Schmidt trigger. Then I wanted to show you one last thing. Oh, I guess it's not associated. So just let me open it up. And so what we have here is, you'll notice here's the integrator, which is part of a quadratic integrate and fire, but it has a reset circuitry. So we still have the same integrator type things. We have integration constants. Reference voltages is when it would switch, right? But it essentially has this ability to compare to a variable reference and then reset itself. So in these circuits, the Schmidt trigger or the resettable integrator, it's all built into one block. You don't need to make your own Schmidt trigger. All right. Then this is actually how you add in the the reset voltage. Because if this resets and this goes to 0, then you add in whatever is here, right? Now these summers are half cycles, so in order to see the output, you got to put a sample and hold. And then the multiplier, they have a multiplier block, and it's a bit of it's very efficient, but it's not a straightforward analog multiplier. And you need a sample and hold to get that to work as well, and you feed that back in, so you get your actual differential equation, nonlinear differential equation. And oops, you can see it spiking. Now the reason why it looks funny is that I'm taking these outputs here, and I would have to convert them to the real output is the difference between these two. So if I actually just moved one of these here, oops, right, oh wait, because it's blue is already there. Okay, so you can see that tangent. Type thing. That's the time domain of a quadratic integrate and fire, and then it stops. It's about to spike, and then it doesn't. All right. I've actually asked the company to pull all of this into one block, one neuron, because even though the chip can handle all these components, you can't fit them into the drawing space. Even though the physical chip can have two multipliers and has more op-amp-based circuits. So that is an introduction to using the quadratic integrate and fire in a Anadigm switch capacitor circuit. We've shown you a filter, doing it made out of fundamental building blocks and then using their building block. If you go back, you can see like here's other ways that you can do it at a much higher level. Like here's a thermocouple signal conditioning example, right? And it'll show you how to set things up. Okay. But that's probably long enough.